Assalamualaikum warahmatullahi wabarakatuh, and good morning to all my students. Okay, so we are now still in topic 8, and in this video we're going to continue our discussion on 8.3, the subtopic of continuity. Okay, so then in this part or in this video, the student should able to explain the continuity of function at a point and compute the continuity of a function at a point. Okay, so now, the key word for this notes, or we call for this subtopic, intuitively a function is said to be continuous if its graph can be drawn over each interval of its domain with continuous motion of the pen without lifting the pen. Okay. So the first one here now, let's say from the beginning until the end here. So let's see whether the graph, we can sketch the graph smooth or not. From here, from the beginning, okay, until here now. And there you go. So I don't need to lift the pen or shift the pen out from the line. Okay, so let's say from here, there you go. It's continuous. And what about this one here now? Okay, I started line from here and then continuing until the end here. Okay, and that's it. It's a continuous because we can sketch the line without any loophole on the line. Okay. And what about this one here now? Okay, I begin from here and look at it. It's very smooth until at this point. Let's say if I make this one as an x equal to an a. From the beginning, everything smooth until here. Then I need to stop, shift up the pen, and begin the journey on here, on this point, and start again here. So this is discontinuous. Okay, there you go. So this is an example of discontinuous line. Okay, discontinuous at a point of x equal to an a. And what about this one here now? Okay, I start from the, we call the line from here, and everything smooth. But then I need to shift up my pen and start all again on the other side. And that's it. So these two lines did not meet each other, so it is discontinuous. And what about this one here now? So start here, so everything smooth until this point here. Then I need to shift a pen and start all over again here. So, and when x exactly equal to an a, then the value of fx is not equal to the limit when x approach to a from left and right. Okay, the limit axis from left and right are equal, but when fx is not exactly equal to the limit, then this is discontinuous. Okay, example of discontinuous here. And also x equal to an a, so let's start, we call the line from here, everything smooth until here. Then I need to shift the pen and start all over again here. Okay, so when x equal to a, the function of fx does not equal which is exactly supposedly here, but then it gives us a different value here. Okay. Okay, so this is discontinuous. Okay, a definition f(x) is to say to be continuous at x equal to an a if and only if fa is defined. So this is the first condition. Second condition, limit f(x) exists, and also limit equal to the function of f when x equal to a, exactly equal to an a. So for the limit exists, please refer to the previous recall videos or notes. So what are we going to do? The first one here, substitute x equal to an a into the function of f(x), and then find out whether limit x approaching to a from the left side is equal to the function of limit of x approaching to a from the right of the function f(x), and second condition equal to the first condition. So first condition and second condition, they must equal. Okay. Okay, so these are all things that you need to remember. Then determine whether the function f(x) is continuous at x equal to -2, 0, 2, and also x equal to 3 for this function. Okay, so let's say for x equal to -2, limit x approaching to -2 from left or from right of the function f(x). Okay, look at this one here. Limit x approaching to -2 from right, okay, equal to, okay, we refer to the value of y, which is equal to 2. And limit x approaching to -2 from left of the function f(x). When x approaching to -2 from left, and the value of y is given here equal to 1. So look at this one here now. Limit x approaching to -2 from left of the function f(x) is not equal to the limit of x approaching to -2 from right of the function f(x). So the limit x approaching to -2 of the function f(x), okay, the limit does not exist. So limit x, okay, the function of f(x), okay, sorry, then f(x) is not continuous at x equal to -2. Okay, we need to consider three things. The first thing is f(x) equal to fa equal to one value. And then the second thing is the limit x must exist. Okay, for x equal to -2, the limit does not exist because the limit are not equal. Okay, the limit does not equal. So the first condition, the limit of f(x) approaching to -2 does not exist. So clear that f(x) is not continuous at x equal to -2. Okay, so then the second one here, x equal to 0. The limit x approaching to 0 from left of the function f(x), okay, equal to, look at this one here now, when x approaching to 0 from left, the graph moving up will be called given the positive infinity. And also when x approaching to 0 from right side, the graph also moving up. Limit of x equal to x approaching to 0 from right of the function fx also giving that positive infinity. Okay. So the limit, we call the limit x fx exists. Limit x approaching to 0 of the function fx exists. Okay, but then when f0 equal to 5, so then limit x approaching to 0 of the function fx is not equal to when x equal to 0, which is equal to 5. Okay, in this case fx is not continuous. At x equal to 0. Okay, so x equal to 2 and x equal to 3. So when x equal to 2, limit x approaching to 2 from left of the function fx. Okay, look at this one here now. X approaching to 2 from left. The graph approaching to one value of y, which is equal to, according to this one, which is equal to 2. And also when x approaching to 2 from right, 2, and the limit x approaching to 2 from right of the function fx also equal to approaching to value of y equal to 2, and when fx equal to exactly 2, when x is exactly 2, also give us a value of y equal to 2. Okay, when these two, okay, for these two we come up with the conclusion that the limit x approaching to 2 of the function fx is exists, and then when fx equal to 2, then y equal to 2. So limit x approaching to 2 of the function fx equal to f2, which is equal to 2. Okay, so we come up with the conclusion that fx is continuous at x equal to 2. There you go. Okay, now for x equal to 3, so then the limit x approaching to 3 from left, x approaching to 3 from left. Okay, look at this one here now. It approaching to the value of y. Let's say I put here which is equal to 3. So limit of this function of fx equal to 3, and also limit x approaching to 3 from right of the function fx. Okay, so when x approaching to 3 from right, okay, look at this one here now. Is also approaching to the value of y, which is equal to 3. So we say that the limit x approaching to 3 of the function fx equal to 3, and it is exists. But then when x is exactly equal to 3, fx exactly equal to 3 here, then the value of y equal to 2, not 3. Okay, so then the limit x approaching to 3 of the function fx, 3, and the function of 3 equal to 2, they are not equal. So they are not equal, so we come up with a conclusion that the function fx is not continuous at x equal to 3. Okay, as we know that we call the function, as we see here, is a fraction. Fraction 3 divided by x minus 1 multiplied with x plus 2. Okay, determine the point where the function is not continuous. As we know that the denominator cannot be equal to 0. So means that x cannot be equal to negative 1 and x cannot be equal to negative 2. Oh, sorry. This one should be 1 here. Okay, x minus 1 equal to 0, then x equal to 1. X plus 2 equal to 0, then x equal to negative 2. So x cannot be equal to 1 and x cannot be equal to negative 2. Okay, the function denominator cannot be equal to 0, then x cannot be equal to 1, x cannot be equal to negative 2. So then f1 and f negative 2 does not exist. Okay, therefore fx is not continuous at x equal to 1 and x equal to negative 2. So when x equal to 1, 1 minus 1 equal to 0, 0 multiplied with any value equal to 0, then 3 over 0 is undefined. Same thing goes to x negative 2 here. Negative 2 plus 2 equal to 0, multiplied with something equal to 0, 3 over 0 is undefined. Okay. Okay, now, look at this one here now. Determine the continuity of, okay, for these two graphs here. Okay, the first one, fx equal to x squared plus 2x plus 1 for x less than 0 and x plus 1 for x that greater than or equal to 0. Okay, at x equal to 0. So let's take a look at the question again. Sketch the graph of the function, hence determine the continuity of f at x equal to 0, and the second is x equal to 2 here. Okay, now, so for this function of fx, okay, we're going to sketch the line graph of x-axis and y-axis first. Sorry. Okay, so the graph of first one then. Okay, so this is the graph of called very smooth, sorry then. Okay, there you go. Okay, the graph touch at the point of x equal to 1 here, negative 1 here, right? Okay, now, this is the graph of x squared plus 2x plus 1. And then, let's take a look at we call the domain of this, which is x less than or less than 0, meaning only the graph for the left, we call less than 0 here, is what we call a variable for the graph of this. So then, okay, so then it's only end up here. Okay, so what are we going to do next is erase the graph with blue or purple in color, and then the graph of x equal to 1. Okay, let's do this one here. The domain is for x greater than or equal to 0. So let's say for y equal to x plus 1, when x equal to 0, y equal to 1. 0, 1 is somewhere around here. And then when y equal to 0, then x equal to negative 1 here. So we come up with this line. There you go. By the way, this graph for x plus 1, fx equal to x plus 1, is valid for x greater than or equal to 0. So it means that for the domain of x positive from 0 to the positive value here, so what are we going to do next is, okay, so I start from this point here, and let's erase the rest of this. There you go. Okay. Okay, so now the graph can be drawn with domain continuous motion of pen without lifting a pen. So it means that here, if we sketch the graph, and at this point, the value of fx equal to 0 is equal to when the limit x approaching to 0 from left and right, which is equal to 1. And then we continue the journey without lifting the pen. So again from here, everything smooth until the end here. Okay, so fx is continuous of x equal to 0. Continuous is at fx is continuous at x equal to 0. Okay. B fx equal to 1 divided by 3x minus 6, where x cannot be equal to 2, and 0 when x equal to 2, and the point at x equal to 2. Okay, we're going to sketch the graph again. Okay, now the y and x axis, so there's an asymptote, vertical asymptote here. Okay, vertical asymptote at x equal to 2, because x cannot be equal to 2, so automatically it tells us there's an the vertical asymptote for the graph. And now let's sketch the graph here using other colors then. Okay, so the graph, there you go, first one then, and then there you go. Okay, this is for negative 1/6, and when x equal to 0, when x equal to 2. Here, y fx equal to 0 when x equal to 2, this is the coordinate of 2 and 0. Okay, so look at this one here now. The graph from the left side is moving down here and did not, recall, meet with the line on the other side, moving up, and when x equal to 2 and the fx equal to 0, it's not a, recall, smooth one line between all these three graphs here. So we come up with a conclusion that fx is not continuous at x equal to 2. Okay, so let's take a look at this one here now. So find the value of k, given fx here, find the value of k is fx is continuous at x equal to 1. Okay, so just imagine that, okay, we are focusing on this. It's a number line where x equal to 1. Okay, so x greater than 1. And this is a domain for kx squared minus 2, and then x less than or equal to 1 for the function of 2 minus x. Okay, so now just imagine that fx approaching to 0 from left side and x approaching to 1 from the right side. X approaching to 1 from the left side and x approaching to 1 from right side. And x equal to 1 for the function of 2 minus x. Okay, here. Now, let's say the first point here, f1. When x is exactly equal to 1, is only valid for 2 minus x, because x less than or equal to 1 is for 2 minus x. So 2 minus 1 equal to 1. Okay, and then we just take one of the limit which is opposite of this from, okay, first just now we test when x equal to 1 from the function of 2 minus x, because it is including 1 here. But then we compare with the limit on the other side of this. Limit x approaching to 1 from right side of kx squared minus 2. Okay, so just imagine that when x approaching to 1 from right side, getting close and close, very close to 1 from right side. So we just assume that the x equal to 1. Just assume, okay, not exactly 1, but assume this is 1 then, minus 2, so then k minus 2. So then because the limit when x approaching to 1 value of the function fx must equal to the function when x exactly equal to that point, which is 1 equal to 1 right now. So then k minus 2 equal to 1. K equal to 3. Okay. Find the value of k for this function here, and h is continuous at x equal to k. Okay. It mentioned in the question that the function of this, and it is continuous at x equal to k. When x equal to k, then hx equal to 6, meaning this function and this value of 6, they are in one line or one graph. Okay, now, okay, hx is continuous at x equal to k, and hk equal to 6. Okay, so please refer to the question again. So first one here, no. Okay, hk equal to 6. Then second part here is limit x approaching to k. Okay, so please refer to the question then. X squared minus k, x squared minus k squared divided by x minus k. So x squared minus k squared divided by x minus k equal to limit x approaching to k, and this one here come out with x minus k and x plus k divided by x minus k. Okay, so simplify this, come up with limit x approaching to k for x plus k. Okay, and then let's compare this and this. So for the third cases here, let x approaching to k. Just imagine that value of x is k. So we substitute k plus k equal to 6, where 2k equal to 6 and k equal to 3. Okay, this means that x approaching to k for this function, it's not that x exactly equal to k, but then we just assume that the value of x is k for a while. Okay, just assume for k for a while, so k plus k equal to 6, then k we get it equal to 3 then here. Okay, now given this one here, okay, so it divides into 3 sections. First, which is 3 and 5. X less than or equal to 3 is for ax squared plus 2, and then here between 3 and 5, the function of bx plus 1, and then greater than 5 equal to 4. Okay, so then find the values of a and b if f is continuous at x equal to 3 and x equal to 5. Okay, we rewrite the question again. So this is the function of fx. So we got ax squared plus 2 for x less than or equal to 3. Then we get bx plus 1 for x lies in between 3 and 5, and then equal to 4 for x greater than or equal to 5. Okay, so now it mentioned in the question that, so find the values of a and b if function f is continuous at x equal to 3 and x equal to 5. Okay, first one here, f is continuous at x equal to 3. Okay, I rewrite the recall, then the one I did mention just now again, 3 and 5. Okay, the first one here is for ax squared plus 2, and this one here for bx plus 1 and equal to 4. Okay, so we look at we look at this one here when x approaching to 3 from left and right. So then for the limit x approaching to 3 from right of the function fx equal to f3. Okay, f3, if we refer to this number line here, so this function of ax squared plus 2 give us exactly, because when x equal to 3 and there is a value here. So then for this one here with a3 squared plus 2 f3, and then x approaching to 3 from right. X approaching to 3 from right, we compare with this one here, which is b3 plus 1. Okay, so if I make this one here, okay, I make some adjustment here. Okay, the limit of x approaching to 3 from right of bx plus 1, and this gives us b3 plus 1 equal to 9a plus 2. Okay, and then 9a, simplify this, I said 9a minus 3b equal to negative 1. Equation 1. Okay. And also f is continuous at x equal to 5. Okay, x exactly equal to 5 for the graph of the function of 4 here. Okay, and we compare with we call limit x approaching to 5 from left. So the limit x approaching to 5 from left, which is bx plus 1 equal to 4. Okay, so then substitute, assume that x equal to 5, just assume bx equal to 5 here, come up with 5b plus 1 equal to 4, then b equal to, okay, this one here, 5b, 1 bring it here become negative, so 3, then b equal to 3 over 5. Okay, so substitute this value of b into here. So 9a minus 3 times 3 over 5 equal to negative 1. Okay, you can use your calculator, is a simultaneous equation with two variables of a and b with two equations. And finally, you get an a equal to 4 over 45. Okay. Next. Okay, exercise given and the final answer is a equal to 2. You may try the questions by yourself, and if you have any problems, so you may refer to me again, or refer to any of your teachers to get the solution for this question. So now, this is all the content of our discussion for this video, for this subtopic then. So first is make sure that fa is defined, limit of the function x approaching to a exists, and make sure that the limit x approaching to a of the function fx must then equal to fa. Then we can say that the function fx is to be continuous at x equal to a. Okay, so that's all for today. I do hope that all of you enjoy this video and you may continue your tutorial. That's all for today. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and have a nice day.